Hello, good morning, everyone. Can you hear me?
I can hear you.
Okay, great. Yeah, I just want to confirm. Yeah, my microphone is no problem. Okay. Yeah. Um, I think everyone did a very good job in the midterm, and I uploaded the grade and score. Right. I think most of you have a good progress so far. And I not uploaded. I extended the assignment 3 right to the weekend. So this is your first programming assignment, and I will ask TA to grade that next week. Hopefully we can upload the grade by next week. Okay, Scott. So anyway, we missed a class in Wednesday, so today I think we will going to start in a new chapter. This chapter is about the network layer. Okay, so let me share my screen. Okay, I think everyone should be able to see the screen. Okay, so let's start. I think I also need to play a video today about some new concept. But anyway, I will share that later. So I think we have already learned the application layer, right? And the transport layer. Okay, so now I think we need to go to a next layer, right? As the title of this class or this textbook, right? From top to down. So let's do it one by one. So today we are talking about the network layer. Our goal is to understand the principle behind the network layer service, focusing on the data plane. We will talk about what is the data plane, what is the control plane, okay? So network layer service model, forwarding versus a routing, and how a route works, and how addressing happening, and generalized forwarding and internet architecture, something we have already mentioned, okay? So first we need to talk about what is a network layer, right? The overview of what network layer. Generally speaking, it consists of data plane and control plane. Okay, so what is the data plane? What is control plane? We'll see that. So what's inside a router? So the router, we have input ports, switching output ports, and buffer management scheduling, something here. Okay, but general idea is um, you have some datagram input, and input ports will how to switch the data to the output transport. There is a forwarding and the routing algorithm here. So we'll generally talk about that. And there is also some buffer management there. Okay. And then the most important thing for the network layer is the IP, right? So TCP IP protocol is as we mentioned before, is the key of the today's internet. So TCP, we have already mentioned that, right? So we spent about more than 1 week to talk about reliable data transfer protocol and the TCP protocol specifically, right? Now we are going to the IP, right? Internet protocol. That's the network layer, okay? So, but anyway, this is something we will cover. And first, what is network service layer service, okay? And the protocol. Oh, okay. So I just try to check this. Joseph, your okay. Yeah, I think it's okay. Yeah, just do assignments. So I think we previously in the site. Sorry to just say something about our class. So previously we see something about the project, but depends on the progress. If we don't have any final project, we will average the project score to the assignments. Okay, so finish assignments, try your best to as much as possible. So I think if you have good assignment score, definitely the overall final grade will not be, bad. Yeah, I believe. Yeah. Anyway, let's just continue. So network layer service protocols here. Here is a quick recall, right? So the right hand side is our very classic, and you have seen that several times, right? This figure several times. It's very classic diagram for the networking class, right? So we have learned the application. Let me change my mouse. Okay, so we have already learned the application transport, and now we are going to the network and the link and the physical. So you can see here the network is a key part, right? Between the application transport and the link and the physical. If we go underneath, the part would be more hardware and physical related, right? So this network layer is quite important to connect the something like a software layer and the hardware layer. Okay. So we can think about the transport segment from sending to receive host. Sender is just encapsulates the segments into datagrams. So just I mentioned, we use a different words for the basic unit in different layer, right? So here is we are using the word datagram, right? In the transport layer, we are using the word packet, right? So here's the datagrams, passes to the link layer, and for the receiver, it delivers the segments to the transport layer, right? So we are using different words, but just speaking, that's a basic unit for that layer. Okay, and then containing the information or message or data, whatever, right? So the network layer protocol in every internet device hosts routers, right? So every device should have this network layer protocol. So and the important parts in this layer is routers, right? Routers plays an important role in this layer. So it examines the header fields in all IP datagrams passing through it, and moves datagram from input port to output ports, transfer datagrams along end-to-end path. So we will give more details about how routers working and how forwarding and how routing algorithm work, okay? But the key part is the router, right? So routers is a very important part in the network layer, forwarding message, routing message, right? Or datagrams to be specific, right? To be precisely here, okay? So the two key network layer function is forwarding function and the routing function, okay? So forwarding function, what is a forwarding function? I think a forwarding function is a move packets from router's input link to appropriate router's output link. And we will explain what's the difference between forwarding and routing. If you look at the words, maybe you are kind of confused. You think, oh, okay, so both of them just move something from somewhere to somewhere, right? But I think the key difference is they are not in the same scope. One is from global view, one is from local view. Okay, so you can see routing here is determining the route taken by packets from the source to the destination. So it's kind of like if you have a forwarding process, it's just like you getting through a single interchange, right? So you're just trying to know from this way to that way, right? In an intersection, right? You want to know which way you need to go, right? But this is just the local view, okay? But for the routing algorithm, it's a process of planning trip from your source to the destination. It's just like you use a Google map, right? You have ahead of time to do a planning, right? But forwarding is just when you're right there, you decide which way you should go. Okay, it's kind of like this analogy. Okay, so this is difference between the forwarding and the routing, but this is the very important two basic functions in the network layer. Okay, so then let's see what is a data plane and what is a control plane. after we understanding forwarding and routing are two important functions in network layer. And the data plan, what is a data plan? What is a control plan? So I think from the word meaning itself, I mean, you can get something here, right? Data plan is just some layer or something, right? To help you manage the data, how to you contact with the data, right? The control is just like you like police, right? Just control how the flow, how the traffic. But here is a precisely precise explanation. So the data plane is a local per router function. So it determines how datagram arriving on router input port is forwarded to the router output port. You can see here value arriving, a packet header, and it determines which way you're going to go, right? So you can think about this data plan is corresponding to the forwarding algorithm, right? But we will talk about how forwarding algorithm works. But anyway, generally speaking here, the data plan is a local per router function, right? When the datagram arrives, it will determines how datagram from the router input port to the router's output port based on the information in the header, okay? So we will give you the idea of IP templates, whatever the header what is, but generally speaking, there is for example here 0, 1, 1, 1, right? To determine you're going to 1, you're going to 2, you're going to 3, right? 0, 1, 1 could be part of the IP address, right? But you based on this header information to determine which parts, which output, not which parts to specifically, it should be the output port of the router, right? Which output port you should forward. Okay, for the control plane is a network-wide logic. Just as I mentioned, it's like it's corresponding to the routing algorithm, right? It's a network-wide logic. It's a global view, right? You need to determine how datagram is routed among routers along end-to-end paths from the source host to destination host, right? So you can think about the data plan and the control plan are two things corresponding to the previously forwarding and routing function, right? So these are two things here. And the two control plane algorithms here we think about is, we know that is a traditional routing algorithm. So it's implemented in the routers, okay? So it's implementing the router itself. So there is some, okay, so here is the point. Even if the routing algorithm is globally, right, is a network-wide logic, it can be implemented in the routers, right? But then you can immediately think about the problem that you only have some local information or something here if you implement it in the routers, right? And sometimes it's to be integrated into the hardware, right? But this may not be the optimal or may not be helpful to do some things. We will show a video what is a better solution could be. So for example, the software defined network. So some of you may heard about that software SDN. So SDN now I think is very hot in a lot of places. Okay, cloud, IoT, many places. Okay, so implemented in the remote server, right? Using a remote server to control the routing algorithm for this network. So you can think about you have another central place, right, or something guide you, right, and you just implement that software defined network and use that to do a routing, to do something for you in this network, not just implementing the router itself. I believe I have I should have oh yeah, I should have a video for you in the next slide. But anyway, here is just a quick description of about the traditional routing algorithm and software-defined networking. So I will have a 3 minutes video to introduce what is the SDN, okay? But here's just a quick mention. Okay, so let's see if there is any question. Okay, seems so far so good. So if you have any question, you can post or you can discuss, okay? So, Okay, let's continue. So per router control plane, it is an individual routing algorithm components in each and every router interact with the control plane. So the idea is just you have the per router, right, control based only on the values in arriving packet header. For example, here, why we forward this message or this let's say a datagram, right, to the link 2, right, or the output port 2, right. So we should have some local table, right. You just look up the table, and then you decide which is the output port, right? So here is for example, you can see here we have the local forwarding table, right? You have header, you have the output, right? So you just do a quick table search, right? For example, here is a 0111. You just search the table and you identify that 2, it should be your output link, right? You just send or forward this to 2. Okay, so this is a per router control, and there is a individual routing algorithm in each and every router interact with the control plane. Okay, so you can see here the routing algorithm sitting beyond all the routers, but it has been implemented in the router level, right? You don't have any other separate server, separate processor to help you to identify, right? Which is the best way, which is optimal or traffic flow, whatever, right? It's just based on the scheme implemented into each router, right? Each router has a forwarding table here. And what is okay, so here you can see that this data plane is just separate with the control plane, right? Control plane is the routing algorithm, and data plane is how you forward the data, how data flows, right? And here is a software defined network. I think, yeah, we can discuss more about this, but from research point of view, this is a very good and hot topic. Even I think in your future career or job, if you are interested in doing something related to networking, software defined network is a good area now. I think many people are talking about that in data center, in HPC center, in IoT scenario. A lot of scenario can use that. So we can see from the video here. I will play that later. Okay. So after I finish this slide, so it's a remote control computes install forwarding tables in routers. Okay, so you just you have the remote control, right? It can do some better optimization for you and forwarding the tables to the router. It's like you not integrate something in the router constantly, right? You have some better forwarding scheme, and you just use the actual server to identify that, and then you just deploy that to your server. Sorry, to our routers, right? I think it's a commonly seen in many cases, right? So sometimes if your traffic is not let's say, okay, let's use the traffic, road traffic, right? So if the traffic lights, right, it's the time is not very I mean, if the time is constant, then the problem is that or the static, right? The control traffic lights is static. That means during the peak time, right? So there is some main road, right? So the traffic is very, very heavy. You should dynamically control that. But every day, every month, every season are different. So you should have some like a control service or transportation service that can identify a better traffic optimization for the different traffic light in different road, right? So they can just send that control to each light, right, to dynamically optimize that. So that's the same idea, right? So in the networking, it's the same, right? So the traffic flow sometimes varying, sometimes totally different. So you should have some actual configuration control to deploy better, right, routing algorithm into your routers. So I think this is something kind of similar, okay? So you have the remote control here, extra server, right? So extra server can deploy what it thinks better, right? Routing algorithm into the router, right? So you have some control plane, right, in the remote controller, and and you just have another data plane, right, underneath. So let's try to see a video here. Let me try to share another screen. I think this video. Okay, let me share the screen. So sorry, hold on 1 second. Okay, I think you can see the screen, right? So let me know if you cannot hear the sound, but let's just play the video first.
In recent years, software-defined networking, or SDN, has emerged as the next big thing in the networking industry. Given all the hype, where are we now? Researchers at Stanford are credited with creating the idea of bringing the tenets of virtualization to networking, and thus creating the software-defined networking market. Traditional networking uses integrated hardware and software to direct traffic across a series of routers and switches. The original use case for SDN was to virtualize the network by separating the control plane that manages the network from the data plane where traffic flows. There is a smart controller running specialized software that manages all network traffic in the data center, and a series of routers and switches that forward packets of traffic. Virtualizing the network comes with advantages. Networks can be spun up and down dynamically, they can be fine-tuned for specific application use cases, and security policies can be installed on each individual network. Today, the SDN market has evolved, and it's breaking out of the data center. SDN is being used in the wide area network to control how enterprises connect to their branch offices. This use case, called SD-WAN, uses software to aggregate multiple types of network connections, such as broadband, MPLS, or wireless, to create strong and cost-effective connections. Micro-segmentation is the idea of using SDN for security. Certain networks can be ultra-secure and carry sensitive data. Other networks can be public-facing. So, if a hacker gets into a public-facing web server, they are restricted to the server segment of the network. This limits the hacker's ability to access any other segments, such as secure data center networks. SDN is also used in an area called Network Function Virtualization, or NFV. This is the idea of replacing specialized hardware like firewalls and load balancers with software running on off-the-shelf server hardware. Some vendors are using SDN to connect data centers to public cloud providers, creating a hybrid cloud network that includes microsegmentation or dynamic scaling abilities. Other SDNs could be used to help manage the deluge of traffic from the Internet of Things, segmenting network traffic and helping to organize the data. SDN has evolved from a specific use case to being applied to many different areas of networking, both within the data center, out to the cloud, and in the new world of IoT. As software is used to control the network, it becomes more agile, easier to manage, and it's ready to adapt to whatever use cases emerge in the future.
Okay, yeah, I think this is a quick introduction video, right? So not too much detail about, let's go back to the slides, sorry. Okay, not too much detail, but I think this is just an idea about how the software-defined network plays an important roles in different applications or different scenario, right? Just as I mentioned, the idea is simple, right? So you have a smarter, more intelligent remote controller, right? To define the routing algorithm or define different security things, right? In the different cloud, HPC, IoT, right? Different areas networking. So anyway, I think this is some new stuff quite being used today, right? Not traditional, just routing algorithm integrate into routers, right? But anyway, let's continue. So network service model here. So what is a network service model for channel or for channel transporting datagrams from sender to receiver? So explanation, example service for individual datagrams. So here we are trying to understand what is the service model for internet for different networks, right? And the example service for individual datagrams, for example, they can guarantee the delivery. They can guarantee the delivery with less than 40 millisecond delay, right? So another example service for flow is in order datagram delivery guarantee minimum bandwidth to flow restriction on change the packet spacing. I think this is something you have already seen before, right? We guarantee something, we cannot guarantee something here. Okay, so network layer service model for the internet, I think the keyword is a best effort. So the QoS guarantees. So for the best effort, it almost means nothing guaranteed. Okay, the quality of service is nothing guaranteed, no guarantee of bandwidth, no guarantee of data loss, order timing, right? So internet best effort service model is no guarantee on successful datagram delivery to destination, timing or order of the delivery, right? Bandwidth available to end-to-end flow. So this you will I mean see in many places QoS is just the quality of service, right? So you can see internet is the best effort service model, right? So you can say here internet is a best effort QoS, right? So like a best effort quality of service model. Okay, so we will see there is some other service model. So I list other tools. Yeah, I don't mean you to remember every detail for the different service model or the quality of service here, right? But just to give you an idea, there is something that different from the general internet, right? So there is some integrated service that can reserve bandwidth along a specific path on the network, right? You just reserve the bandwidth because this bandwidth needs to be used for other application or special application, right? So applications ask the network for resource reservation and the network device. Sorry, I think I should use annotation here. Okay, so application, let's try to use another. Okay, the application asks the network for resource reservation and the network service monitor the flows of packets, right? So then it has a better guarantee of the bandwidth compared to the best effort, right, service model. But I mean, this is just a different service model, right? But why we use the best effort for internet? So that's the question, right? So a quick answer, I think, is more general, right? So internet is I have another slide talking about that, but general idea is that for internet, it's for general situation. You shouldn't reserve something for anyone for any application, right? But for some specific cases, right, you should reserve some bandwidth for some specific application, right? And there is a differentiated service like is a service model where network elements such as the router and switch are configured to service multiple classes of traffic with different priorities, right? So network traffic must be divided into classes based on a company's requirements. So you have the different classes, you have the different traffic, you have the different priority, right? But anyway, these are the two different models. There is no requirement for you to understand this very deeply or remember this different difference between the integrated service and the differentiated service. But the idea for, sorry, where is my mouse? Oops. Okay, sorry, I don't know why. Okay, here it is. Okay, so so the reflection why we need to use a best effort service. right? So I think it's hard to argue that the best effort service for internet is successful, right? So you allow a lot of things, right? This is a simple mechanism allow the internet to be widely deployed, right? You don't need to specify or restrict anything, right? But there is some benefits. I don't want to go through that in details, but generally speaking, this helps the internet to become widely used and successful because you just provide bandwidth to different application in fair, right? So you don't prioritize what application prioritizes what kind of class, right? But anyway, I think for the first topic, network layer overview, the most important thing for you is to understand the data plane, the control plane, the routing algorithm, not the routing algorithm, but what is the routing in general, right? What is forwarding in general, right? And you think about data plane corresponding to forwarding, control plane, right? To overall routing, right? And software-defined network and traditional networking, right? So anyway, I think let's try to finish this next topic for today. And the router architecture overview is a high-level view of the generic router architecture. It look like this way, right? So you have the router input ports, and you have the router output ports, and you have a high-speed switching fabric between them. And the router processor is just sitting between the router input ports and router output ports, right, to control the input of how to forward, right, how to forward from the input port to output port. Okay, so here is another thing, right? So we just mentioned routing corresponding to the control plane, forwarding corresponding to the data plane, and they are also corresponding or mapping with different software and hardware layer. So for example, here, so routing management control plane is mostly software layer, right? So because as I mentioned, you can use a remote server to control the routing algorithm. That means that mostly it's software, right? It's a software determining how routing would be functional, right? But for the forwarding, generally speaking, mostly it's in hardware component, right? The hardware controls, operates how forward the datagram. And this would be in a nanosecond time frame, but software would be in millisecond time frame, right? So you can see the hardware always be much faster than software, but software is people can program that, right? People can control that. People can do a lot of things with that. But the hardware, after you deploy it, then nothing can be changed, right? But so that's why there is a hot topic today. I think is I'm not sure if you hear about that. It's smart NIC, smart network interface card. That's a good hardware. That hardware can do like a FPGA, right? Can do some programming in the hardware, right? But that's some new technology. But generally speaking, hardware is like CPU, GPU, right? So after you fix that, it's a fixed, right? And but now people are trying to make a more programming inside the networking, right? The good thing is that you can control networking, right? Depends on different application, different traffic, right? But anyway, that's another topic. Here is the routing and the forwarding corresponding to control and data and software and hardware in a different time scale, right? So the input port function here, so just quickly go through that. So you have the physical layer, link layer, right? Physical layer, bit level reception. The link layer is the Ethernet. We will cover that later, right? Because we are still in the upper layer. And the lookup forwarding is just I mentioned, you have a lookup table. You have to, based on the lookup table, to forward, right? To forward to the output port. And this is a decentralized switching, Okay, you're using header field value, lookup output port using the forwarding table in input port memory, right? So it's like a match plus action, right? You just find that using the match lookup table in the port memory, right? And then forward that. So the goal is a complete input port processing at line speed. I mean, the key the key part here is to provide a very high line speed, right? So you see that before, right? We need to have a very fast forwarding speed in the router, right? Otherwise the delay would be very high. So it needs to be at a line speed. Line speed, like you just do something in streaming, right? You take a datagram and immediately you should be able to process that and forward that to the next, right? So the input port queue, so if datagrams are arriving faster than the forwarding rate into switch fabric, then you have to have a queue. But the ideal case that we don't want to have the very full queue, right? Full occupied queue. So you have to have some similar speed between the datagram arriving and the forwarding rate. Okay. So there are two different forwarding scheme. One is a destination-based forwarding. One is a generalized forwarding. The traditional way is that you forward based on only the destination IP. Okay, so this is some simple traditional method. But another is a forward based on any set of the header field values. But anyway, I think we just focus on the IP address based forwarding, right? You just look at the IP and then you know which is the next you need to forward to. Okay. So I think another important thing here is the destination-based forwarding, how you can use the table, the destination address range to know which link interface you need to go, right? And generally speaking, right? So you allocate the address range very evenly, but this is not something always be happening, okay? So here is the important algorithm. I hope you can remember. But before I introduce that algorithm, here is the situation, right? So this is the ideal table. Okay, every link face is corresponding to some destination address range, and they are allocated kind of evenly, right? But this is not always the case, as I mentioned. What happens if the range do not divide up so nicely, right? So what if, for example, something originally need to be allocated to the link interface 3, but now just be allocating to the link face interface 0, right? So definitely you can argue that, oh, we can set up another sub interface within 0 to do something, right? But this is a little bit complicated, right? So if we have this situation happening, how should we deal with that, right? So is there any way to fix that? So then we propose algorithm. I think this algorithm is quite straightforward, but let's try to remember this, okay? In some homework assignments or the exam, there will be some related questions. So it's the longest prefix in matching. So it's just based on the word, it's just when you're looking for the forwarding table entry for given destination address, use the longest address prefix that matches destination address. What does this mean? Longest address prefix that matches destination address. So everyone here should know the prefix, right? So the longest prefix is when you do a match, you're just trying to find what is the longest address prefix. Because you could have several matches, right? But which is the longest one, right? You should do. So this is the algorithm trying to describe. Anyway, let's see example here. So the question is these two examples. which interface, the first one and second one, should go. I give you some time to see. So first one, which interface, and second one, which interface, based on the longest prefix matching algorithm. Anyone know that? You can just tell me in the chat for first one. It's just based on the description, right? The longest address prefix for the first one is what?
The one in the middle?
For the first one, for this one, sorry, I think I should. For this one, you think it's the middle, right? But for the middle, the problem is that 101 is not matching with the 000, right? Oh, sorry. I missed that. Okay, so here. The problem is that you can see 0001, 0001. These 4 digits are matched, but you can see here is a 1000. This is a 0110. So for the star means that you don't need to match, right? Anything here is fine. We just want to match the listed bits here. So for the first one, I think it should be 0, right? Oh yeah, Scott, you mentioned that. Yeah, it should be this first link, right? The linked interface for 1, because you can see if you search the prefix, right? So here until 1, everything is good, and then you look up 0110. Right. So you can say 0110 is matched with this one, right? It's 0. The 1 and 2 is the 1, right? Are 1. So you should match with the first one. So what about second one? So you based on what I just described. So the second one is the 0001, and you can see the 100. You can see the both matched with the 1 and 2. Yes, you are right. Bryce, you are right. Yes, stars means anything you can be there. It just do not need to be matched, right? Anything. Okay. So what about the second one? Any confusion? So I hope you can give the answer. So any confusion? So if you don't have a confusion, what about the second one? Let's first just eliminate the first one, right? Because you can see here from the 5th digit, it's 1, right? So here is 0. So you should choose between 1 and 2. So 1 or 2. Yes, it should be 1, right? Because 1 is the longest prefix, right? So this means anything could be matched with 2. But here, 1, you specifically mentioned 1000. So 1000 is matched with 1. Okay, so here is anyway, it's an animation. So for the first one, it should be matched with 0. Okay, for the second one, there are 2 matches, right? So 1 and 2 are both matched, but our idea is to find the longest match, longest address prefix that matches. Okay, so it should be 1. Although both of them, 1 and 2, are matched with this address, right? But the link face interface 1 is the longest one. Okay. Is there any question about this algorithm? I think this is not difficult, but maybe I didn't explain that clearly. Star means that yes, no constraint, no restriction. Okay, so you are using the longest address prefix that matches destination address can help you to avoid there is some unevenly distributed cases. Okay, so this is the algorithm we are using at least in some traditional scenario. Okay, so we will see why longest matching is used shortly when we starting address. Okay, but here is a quick solution. Okay, we will talk about how it will help you in some detail. But anyway, this is the algorithm you will use, and the longest prefix matching. Sorry, I think I need to close something, otherwise it blocks my slides. Oops, it's a. Okay, so longest prefix matching often performed using the ternary content addresses memories. So we will mention that later. It doesn't matter. Okay, let's try to finish the last two slides, and we can finish today. So the switch fabrics, right? So transfer packet from the input link to appropriate output link. The switching rate, as I mentioned, right? Rate at which packets can be transferred from input to outputs, right? Often measured as a multiple of input and output line rate. So if there is an n input switching rate, n times line rate desirable. Okay, so they can do something in parallel, right? Because there could be some different links here, right? From n input ports to n output ports. Okay, and the three major types of switching fabrics here: memory, bus, and the interconnection network. Okay, so before I go to some next slides, I think it's just based on these diagrams. I think you can guess, right? What's the difference between memory? What's the difference between bus? What's the difference between them and the interconnection network, right? So I think my guess is that memory, right? Memory just like a traditional CPU, right? If you want to do some switch things here, you just rely on the memory, right? Exchange the data, okay? Put the data, put something in the memory, and then you calculate something, and then just output that, right? But bus is like a PCIe or something, right? And not PCIe, sorry. It's just like a traditional computer systems bus, right? And the interconnect network. So here, so let's just quickly see switching through the memory. So first generation routers, the traditionally computer with switching and the direct control of CPU, right? You just use something like a memory and CPU here. The packet copied to system's memory, okay? And then you can see, you will know, okay, you save in the memory, and then you just know which is the output port based on the table saved in the memory, right? And you just pass the datagram to the output port, okay? So this is something like you transfer the packet, you transfer the datagram through the system's memory, and the problem is that the speed would be limited by the memory bandwidth. Okay, so memory sometimes maybe some of you think that's fast, but based on our research experience, CPU memory could be not such fast. It could be just like tens of gigabytes per second. Even compared with the GPU memory, it's much slower, because if you pay attention to new technology from NVIDIA, the GPU memory could be like 900 gigabytes, or even now more than 1 terabytes per second. But CPU memory is not like this way, right? And also that's a powerful CPU, right? So if you are using some embedded CPU, the memory could be very speed could be very limited. So that's why this is the first generation. But that's when you invent something, right? So you are just use traditional CPU processor and memory to do the routing within the routers, right? You just try to integrate some chips into the routers, right? But this is a how you invent something. And then you can just switch through the bus, the datagram from input port memory to output memory through the shared bus. The bus connection, switching speed limited by bus bandwidth, right? You send the data through something, then the speed will be limited by the bandwidth of something, right? That's the idea. But the bus bandwidth is much higher than the CPU, right? So it still could be several tens of gigabits per second, but it's sufficient, good enough for the access routers, but not like embedded CPU memories are, right? So I'm talking about tens of gigabytes. That's the server CPU memory bandwidth, but for embedded system, I believe it's just maybe several gigabits per second. That's or even megabyte per second. That's very limited. And the final way is through the interconnection network. Okay. Oh, sorry, I think I over time. Sorry, I didn't pay attention now. Anyway, we can talk about this later, okay? And I will upload the slides so you can look up the slides before the class next week. And if you have any question regarding assignment 3, send me and TA email. Yesterday, I remember some students sent me an email about the office hour, but it's sorry, yesterday I have a conflict a time with my office hour. So in case in the future this thing happens, so please just send me email maybe 10 minutes before the office hour, and I can make sure I will be there, or I won't be there, but I will let you know. Okay, so I appreciate that. Okay.
If we have questions about our midterm grade, were you the one who graded the midterms, or was the TA the one who graded them?
Okay, this is a good question. So TA grades that. So you first discuss with the TA because TA grades that. But if you cannot get agreement or TA thinks this question is questionable, so he will discuss with me, and I will let you know, or will let TA know. Okay, but TA directly grades that. So first discuss with TA.
Okay, thank you. Yeah, I'll go to his office hours. It took me a while to find the link, but I saw you sent them in an email a while ago.
Yeah, I think I put in the announcement. So just check the announcement. I don't, that's why I send in an announcement. I'm not sending an email because you can easily check in the announcement in the Blackboard.
Thank you.
Thank you. Okay, thank you, Ace. Okay, so if there is no questions, so hope everyone have a good weekend. Oh, thank you. Have a good day. Bye-bye.